Hey guys, welcome back to another episode of Tuber Teaches. I made an oopsie in recording this, so I'm re-recording it again. Um, but today's topic is the electrolysis of aqueous salt solutions. Um, in Sanadable, we did study electrolysis. However, we basically limited our study to molten salts, which are easy to work with because it's just the opposite of the formation of the salt. So here, um, the problem with electrolyzing aqueous solutions is that water itself can undergo electrolysis. Um, Here is the equation of the here is that equation, the overall redox equation for the electrolysis of water. This thing here, which is simplified to that, 2 water plus what, which is simplifies to that. Um, Now that poses a bit of a problem, and then you also have to consider too the electrodes themselves can also partake in the reaction. Now, when you consider all these things, how do you even go about so generally you're asked to determine what the final products are and what's the net reaction. Now the question is, how the fuck do you even do that? um, the way I like to do it is I like to make a table of cathode and anode and then consider all the possibilities and then choose the ones that are the most spontaneous, so they have the most positive cell potential or the least negative cell potentials, the two half reactions that have the highest cell potential. So let's go through a worked example and maybe I'll show you what I mean. So here we have the electrolysis of, let's consider the electrolysis of nickel difluoride. Right? Pause the video now if you want to try it. Pause the video now if you want to try it, and come back in 3, 2, 1. All right, so you're presumably back. So let's first make our table. So we go cathode.
Okay, so I just downloaded.
Sorry about that. Uh, Sorry about that. That was just my sister. Uh, she'll come back to me later. Uh, Anyways, where was I? Yeah, cathode and anode. And firstly, I'd like to. First, I consider the half reactions associated with the salt. So, at the cathode is reduction. So, no, oops. Ni2 plus 2 electrons gives me nickel. And then, lastly, 2F minus gives me F2 plus 2 electrons. And the cell potentials for each of those reactions are given in this table, which, according to my table here of cell potentials, this has a potential of minus 0.23, and this would have a potential of minus 2.87. Right, now let's consider the half reactions associated with water. Um, I'm going to start on the cathode side, and the way I do this is I look at my table and I look for where water is being reduced. So here I immediately spot a reaction, which is 2H2O plus 2E, which goes into H2 plus 2OH. And the cell potential associated with that is negative 0.83. Maybe I should list these to make it a little bit more clear what I'm doing. That should be a 1 in there. Not 11. 1. So, and then I look for other reactions that could happen at the cathode with respect to water. And although it's not immediately obvious, there's another one here, which 2H2O. No, that's an oxidation half reaction. I look for other ones involving water. So on the reactant side, and I can't find any, so I'm going to stop there. So yeah, I'm going to stop there. Now when I consider the other side, what if I consider the other side for a moment? So, wait a moment. No, there's another half reaction here associated. O2 plus H2, H2O. Sorry, no, I'm confusing myself here. Just give me a moment to think. All right, well, it doesn't matter. The other, now let's consider the other side. So we have 2, which is 2H2O yielding, if I look here on my table, 1.23, 4H plus 4 electrons plus O2 gas, and the voltage for this half cell is 1 minus 1.23. There's another reaction you have to consider, but its cell potential is like minus 1.78. It doesn't really matter in the grand scheme of things. Oh, it's an oxidation half reaction. And the other one here, just for the sake of me including it, H2O yields H2O2 2 plus H2H 2H plus 2 electrons. This one has a cell potential of negative 1.78. So now that we've listed all our possibilities, pick the two. Now we can go consider the cathode side. Which one is the highest cell potential? Negative 0.83, negative 0.23. This one is the clear winner. And then on the anode side, negative 2.87, negative 1.23, and negative 1.78. This one is the clear winner. Right? So that's how you do it on sort of like a paper 2, for example. Let me switch back to my not table. All right. So now that you know how to do it on a paper 2, there poses one problem. They tend to ask this on paper 1, and I don't think it's fair, but how would you answer it for paper 1? Now, the way I go about it is I would use my knowledge of displacement reactions. So you always consider that oxygen and hydrogen will be at the anode, and at the anode, and hydrogen will always form at the cathode. That's just how these things work, right? You can use your knowledge of periodic trends to build yourself sort of an activity series, and then you use the displacement of the activity series to determine what goes where. Now, let's say, for example, we had concentrated sodium chloride solution in water. Now, firstly, I would again split my things, cathode and anode, make a chart, and consider the possible products on each side. So sodium and oxygen. Now, it just so happens that chlorine and oxygen. Halogens generally tend to be favored because they have lower ionization energies. Remember that at the anode you have to undergo oxidation, and you therefore want to have the lowest ionization energy. And chlorine has a lower ionization energy than oxygen, so therefore chlorine is the one that's obviously picked. And it's more than that. We can generalize it to the halogens. Assuming they're of high enough concentration, they tend to be favored when compared to oxygen. Lastly, and then now let's consider the anode side. So we have hydrogen and the metal. Now, it wants to be reduced. The metal wants to be reduced, so therefore we want to look for the thing with the highest electronegativity. Um, Hydrogen has a higher electronegativity than most metals, so therefore hydrogen is what forms at the cathode, anode, whatever it was, the other electrode. So therefore your products are chlorine on one electrode and hydrogen on the other electrode. If it's a dilute salt, it's just essentially the electrolysis of water. But you would use that sort of logic to determine the products. The last thing I want to talk about here is electroplating and factors that affect the amount of product from electrolysis. So, electroplating is plating a layer of metal on an object. Um, you basically undergo this setup here, where you have a silver electrode, a silver solution, which you want to electroplate with silver, and you put the object you want to put as the cathode. And if you hook a battery up, it'll undergo electrolysis. This here will oxidize to form aqueous silver, and it'll reduce on the surface of this to it'll reduce on the surface of this to the metal ions here will reduce on the surface to form a thin layer of metal on that object. So although there's no net reaction, you've essentially made a small thin layer of metal on the thing you want to coat. And this is really important because you can make your silverware look nicer, or put a anti-corrosive layer on something, and so on and so forth. Lastly, let's consider the amount of products from electrolysis. These things depend on the current applied, the duration of the electrolysis, and the charge on the ion. Now, let me go through each of these one by one. The current applied, current is just the amount of charge flowing per unit time, or the amount of electrons that flow per unit time. If you have more electrons flowing per unit time, it makes sense that you get more stuff, since more things can be reduced per unit time. Similarly, the duration of the electrolysis, if you let it go longer, you get more product because you let the reaction go longer, therefore more electrons can transfer and so on. Lastly, when you consider the charge of the ion, this one is not quite as obvious, but it's still pretty easy to understand. If you have a higher charged ion, it takes more electrons to reduce it, so the higher the charge on the ion, the less product you get, since you need to put more electrons in to reduce it fully. And then you can do some calculations here to get a quantitative amount rather than a qualitative description of how much would be formed theoretically by doing this. So you have 45 minutes at a current of 250 amps. Remember, an amp is just a coulomb per second. 60 seconds in 1 minute. 250 coulombs a second. Here you use the Faraday constant to convert into moles of electrons. Note that it takes 3 moles of electrons to reduce a mole of Al3 plus to just Al, and then you get multiplied by the molar mass, and you get that. And that's all for today, folks. Thank you very much.